Now let us see what happens in the moment of inertia for calculation. How to find now? We have seen that okay, I have to use I effective. Now let's say how we can, and we said I effective we have to use, and we are saying that it's not, it does not change much. Okay, though it is change, it's not change. We are assuming that it's not going to change much. Okay, so let's say if I'm looking at the point A, I'm having this flexural rigidity of E and I gross, right? And E is not going to change. Now, when the moment is equal to yielding, okay, which is the point C, this is your yield point. That means the longitudinal reinforcement on the tension side has yielded, right? So when I connect that moment and I calculate the curvature corresponding to that yielding, we know how to do moment curvature analysis. Then I take that slope. So that is basically I'm taking that as EI cracked, and in this case we are trying to be a little bit more conservative, and we are taking 85% of that EI cracking as corresponding to that of yielding moment, right? Now, depending upon your moment that it is acting, okay, I can have this yellow color curve with EI effective like this, or I can also have one more curve. So this is what we are saying. So basically, now what we are saying here is, okay, so between these 2 points, now if I assume a trilinear response your moment curvature, which we can do, either you can do bilinear approximation or trilinear approximation. In trilinear approximation, when I do, I can take from here to here, right? And then I can connect to this, and then you have this, which is D. So this is your cracking, this is your yielding, and this can be your ultimate. Now, how do we get that ultimate point? When we did moment curvature analysis, we keep epsilon cu equal to 0.0035. Okay, and then we did. And for the section that we have considered in the very first example of 1200 mm square, you will find that the difference between ultimate moment and yielding moment was not much. So that is the reason this kind of a between yielding and ultimate, I keep it to be same value, right? So it's an assumption. It's a trilinear assumptions. Now, if I made this to make this trilinear assumptions for any other moment that is subjected like this, okay. For example, this is the moment that we are looking at, which is a service moment. Then I can calculate from this using the slope what would be my EI effective. Okay. So now if I do this point, if I connect this, so basically I can get this slope, okay, and then I can get this slope, so I can get your effective slope. So let us see now. At this point at A, we can calculate your curvature at cracking, right? Similarly, at this point, now how do we get your at B point? Let me erase this. Okay, at B point, let's see what is the difference in moment. Now the moment has exceeded cracking moment by this magnitude, okay, which is m minus mcr. So what would be this slope? You'll find that this increase in curvature from we are interested in calculating this curvature. So now how is this? I have to use this slope, which is the difference in moment is m minus mcr, and this I am using as 0.85 EICL. So that is your additional curvature that I'm getting. Now, what is the total curvature or EI effective that I need to use? It is going to be m by this, right, plus this additional curvature, which is this, right? So if you look at this, is going to be your EI effective, which is this. Okay, we have taken this slope, which is EI effective. Okay, or in other words, for a moment for M cracking, so what we are looking at here is M by phi R is going to be your curvature at cracking like this. So you get, this is your additional curvature that what we are getting. So what is the total effective? A effective is going to be applied service moment divided by the curvature. So I'm interested in calculating this P. Now how do we get this P? This P is summation of PCR plus M minus MCR by 0.85 ERCR. Okay, so that is what your P is. Okay, the moment I get this, I can, because this slope is what we are interested in. Now, what is this slope? So basically, it is going to be moment divided by that curvature. Now, that curvature has two components. One is curvature at cracking plus that additional curvature that is coming because now I have exceeded that cracking moment, right? So for that slope, we are using EI because this is a linear curve that we assume. In this zone, whatever may be the moment, I have to follow this slope, which is between that of these two extremes, right? So this is the way we get your effective flexural rigidity. So again, what is a cracking moment? So your modulus of rupture multiplied your section modulus. So we can get that. And FCR, we take it as zero point 0.7 square root of FCK. So you can calculate your phi cracking as M cracking divided by your moment of inertia. Or in other words, it is going to be EIGR. Right? So that is your curvature. Right. So now let's see. So basically, using this trilinear moment curvature relationship, we took one extreme of when M is less than M cracking, your flexure rigidity EIGR. When it is at yielding, it is going to be 0.85 EICR. Okay, 85% of a cracked moment of inertia we are taking. Between that, when your service moments are between M cracking and M yield, I am going to take this trilinear assumption, and then using that slope, I can calculate your total curvature for that particular applied moment. Then you moment divided by that curvature will give me the effective flexural rigidity, right? So let's see how that moment of inertia is going. So this is the equation that we derived, right? So for any service moment, so this is basically phi cracking plus that additional curvature, okay, additional curvature, right? So that is what this is. Now, what the code is saying is, and we have said that okay, E is not going to change much under service loads. Okay, and so we have seen that elastic modulus up to 40% of its peak compressive strength. It's pretty much linear. Then it becomes non-linear. Though it becomes non-linear, it's not going to change much. When your service stress levels are you're talking about 60% of your peak strength, there will be small reduction, but the reduction is not much. So we're going to assume that the E is not going to change much. The major change occurs only in your moment of inertia. So somehow can I find, instead of dealing with, so can I find a simplified expression for your I effective is what we are looking at. Now let us see what is I effective. So what the code is saying is we can simplify this equation. Okay, because P cracking again we can write that as M cracking divided by EIG, right? So I gross or IG, we can write that. So this and E everywhere we can cancel that, and we can derive a simplified expression only for this effective moment of inertia as I cracking divided by 1.2 minus M cracking by M times eta. Now what is this eta factor? Eta factor is given as, so because 1 by 0.85, okay, is roughly approximated to 1.2. Okay, similarly we are saying that again eta that we are saying. So again, what is that we are doing now? Phi cracking can be written as M cracking divided by E into I gross. Okay, see, in this way, if I substitute for phi cracking as M cracking by I gross, and then if I try to simplify and I cancel E on both sides, I can derive this expression for I effective as like this. Okay, in a simplified form, with eta is taken as 1.2 minus ICR by IGR, which is your gross moment of inertia. Right. Now, what IS code is saying is, okay, can I relate that this relationship between cracked moment of inertia and gross moment of inertia as a function of your neutral axis depth? And this is what we have done is for rectangular section. Now, when I have a flanged section, I will have a large compression width. So your neutral axis will further go down. So somehow I can bring in and find a simplified expression for your relationship between I cracked and I gross. Okay, so that is being expressed in terms of this simplified expression, which is given as lever arm in moment resistance. Z is your lever arm, and X is your neutral axis depth using your working stress method, and BW by B. Okay, what is BW? When you have a flanged section, it is going to be the width of the web, and B is your breadth of your compression phase. It could be the width of your T section, the top flange width, right? So the eta is the actual equation is this. Okay. Again, this is the actual equation. We are saying that E does not change, and I can take this equation and simplify this to this. But again, you are ending up with one eta factor, which is 1.2 minus I cracked by I gross. Then again, the code is saying, okay, I want to keep it as a simplified expression. So the eta can be expressed in terms of your neutral axis depth at service moment and the lever arm in this simplified form. Okay, so these factors actually it is accounting for that I cracked by I gross. Okay, that's what it is. Okay, this and this is the actual form, and this has been converted into this. Because we know that the ratio between I cracked and I gross can be expressed in terms of lever arm and neutral axis depth, and this is the equation that we have come up with for eta. So if you are using IS code method of calculation, so we can put eta like this. Okay, so again, to calculate your flexure rigidity, we are assuming that E is not going to change, only I am calculating I effective. Actually it is an effective flexure rigidity, but we are saying that E is not going to change. I am dealing only in terms of I effective, which is again function of your applied moment and the eta factor, which is the ratio of I cracked to I gross. Okay, now let us see again, I effective from moment curvature point of view, we can do for one cross section analysis using this. Now for deflections, I need to put EI value for the entire member. So which cross section that I consider? Okay, so if you have a simply supported beam itself, we know that you will have cracking only in the midspan region. Other region you will have no cracking. So there is a variations in your moment of inertia along the length of the member, depending upon what kind of moment profile that you are having. So that has to be taken into account. So how do we do that? So we are going to use what we are going to use is an average moment, effective moment of inertia. Let's say for a continuous beam like this, as we have seen, you get cracking like this, right? And if you look at this region, the moment profile also, and this is a case of a propped cantilever. Again, what kind of cracking? You will have only cracking here at the negative region and some positive cracking. And here it's a moment is zero, so there is no cracking. So depending upon now why is that? So basically, if you see here, your moment profile when you plot it here, so you're going to get this kind of a moment profile, right? Now if you see this distance is going to be up to point of contraflexion is going to be 0.15 L. Okay, this region is also going to be 0.15 L, and this middle region is going to be how much? Is going to be 0.7 L. 0.7. So this is 0.1. This. So that is the reason the code is saying that the moment distribution for a fixed beam, you're going to have negative moment for 15% of the span length on the left and right, and the middle 70% of the span will be subjected to sagging moment or a positive moment that is going to induce tension on the bottom side. So the code is taking, okay, I'm going to take 70% of effective moment of inertia, what I'm getting for that section in the midspan, and 15 percentage of what I'm going to get for I effective. So this should not be there. 0.7 should not be there. Okay, so it should be 0.15 of effective moment of inertia at this two supports, because the two supports you can have different reinforcement also. But if you are having symmetrical reinforcement, I effective 1 and I effective 2 will be same, right? So this is the way we are going to get effective moment of inertia for the entire length of the beam. And Now, when you have a propped cantilever, again, what is it you're saying? This 15% is where I'm going to have negative moment. Remaining 0.85 L, I'm going to have positive moment, right? So that is the reason the code is saying that you take this middle effective amount of inertia, and I'm taking 0.85 for that and 0.15 for this support. So it's basically some weighted average depending upon the moment profile what you're going to get. Okay, so this is the way that I effective is calculated for continuous patch. So what you said again, if you go back, actually from cross section analysis point of view, EI effective I can calculate if you do the moment curvature analysis. But deflection is a member level property, and you are going to have different moment curvature relationship for different sections along the length of the member. So, and we said that though I need to calculate EI effective average, E is not going to change. So we are calculating only effective moment of inertia. For that, for a continuous system, we came up with this average I effective like this. For a propped cantilever, we came up with 0.85 I effective of at midspan plus 0.15 I effective at continuous support. Right? So in this way, we can calculate your effective moment of inertia. So that again, you can calculate that as this is your average cracked moment of inertia divided by. So again, we go back to this. So this is what I effective. Now this is for the member level. Then how do we do? So you have to put I cracked of average and then M cracking by M times eta. These all these factors I have to take in terms of some weighted average. So how do we get that? So you see here for all this M cracked average, the M, all these things we are going to take it in terms of some weighted average function like this. Now what is K1 and XM and X1 and X2? So you can see here for moment also I can take if I assume some K1 weighing factor between 0 and 1, that again depends upon what is the ratio of corresponding fixed end moments that you are going to have. Okay, so MF1 in this case, if you look at it, MF2 here is 0, here you will get some value. So if you take based on this the ratio of the sum of the corresponding fixed end moments, I can find this weighting average factor K that is going to vary between 0 to 1. So depending upon the moment profile I can have, I can find this K. Okay, so once I find that K, using that K, I can calculate your I cracked average, because again I cracked average also can change. You can have cracked moment of inertia is going to change because your reinforcements are going to be different at left support, right support, and midspan, right? Similarly, moment also is going to be what is the moment that you are going to use. You have to take an average moment. So, what kind of average moment that you will take based on this weighted average function. So, this X can be for moment cracking or it can be for your moment at service. So, using those things, we can get what kind of moment and what kind of cracked moment of inertia and eta factors that we need to use in your I effective equation, right? So those the ratios of these moments are given in table 21 of our code. So using that, we can find your weighting factor, okay, which again depends upon the ratio of some of the fixed end moments that you are having, depending upon the conditions, fixity that you have at your two ends. Okay, so you can see the subscript 1 and 2, they denote two continuous support locations, and M denotes the midspan location. Okay, so that we have seen. Okay, so this is a factor at midspan, this is at first support, and this is your second support. So again, K1, depending upon MF1 and MF2, I can find what is K. Okay, we will do an example and it will become clear. Right. So this is our IS code method of calculation. Now let us see how the British code provisions are doing this calculations. Right. So these are called effective, again effective curvature formulation. We are going to look at British code provisions. Now British code it considers that curvature at any section should be taken as larger of the values that are obtained from uncracked section and cracked section analysis. Okay. Now we'll see what is an uncracked section analysis and cracked section analysis. So you find curvature for uncracked condition and cracked condition, whichever is larger. Okay, that should be taken in your calculation. So let us see now how it is. Now what this the code is saying is, even if your applied bending moment is less than the cracking moment, the section may behave as a cracked one due to prior heavier loading or cracking. Sometimes in the past, your current service loads may be less, but in the past you may have an accidental overloading. So because of that, you might have already cracked. So what the code is saying is, it is prudent to use cracked section analysis for calculating the curvature, effective curvature that need to be used for deflection calculations. Or it is also saying that you may have cracking due to temperature and other shrinkage effects which you cannot completely avoid. So it is the British code is saying that you always better to take cracked section analysis for calculating deflection. So let us see now what are these things. So this is what we consider. Okay. So this is your effective curvature. So you are going to take two types of analysis. One is your stress in an uncracked section. Now, how do we get the stress in uncracked section? So what we do is, the code is saying that you keep the stress in the concrete at the level of C, which is your FCTS, stress in the concrete at the level of your tension steel, as either 1 megapascal or 0.55 megapascal. I am going to fix that value. Okay, depending upon whether I am calculating short-term deflection or long-term deflection, this FCTS is taken as 0.55 or 1 megapascal. Okay. Once I fix that limit, now the stress at the level of your steel is going to be modular ratio times your stress in the concrete, which I am fixing. That's what the code is asking you to fix that level. Okay. Though you may have uncracked, you may find that in uncracked stage, ideally what would be the bottommost stress as per our this? It will crack only when your stress at the bottom becomes FCR, which is zero point 0.7 square root of FCK, right? However, the code is not allowing you to do the analysis at that stress. It is going to take at the level of steel. I'm going to, for example, for 40 megapascal FCK, what is FCR? You will work out to be zero point 0.7, let's say square root of 40. Okay, you'll find that it will be 4.7 or something. Okay, so which will be much higher value at cracking. But however, the code is saying that it is you take only at the level of steel a stress of 0.55 or 1 megapascal, depending upon whether you're doing short term or long term deflection. So that is the stress that we are going to fix. In the cracked section analysis, okay, again, so if you do that, then for the first, let's say, phi effective, how do we get that phi effective? Let's say this is your x, so this is your phi. Okay, p effective. Now what is p effective? Fc by, sorry, epsilon c by, this is epsilon c by um, x. So this is the distance, this is the slope, right? So this is your phi effective. Now I can relate epsilon c as Fc by Ec, because we are doing serviceability checks. We are going to assume that the materials are going to behave in a linear elastic fashion. So if I know strain, I can get my stress. But we are going to assume the stresses and back calculate my strain. So uh, now how do you find this Fc? I have to put this value as 0.55 or 1 megapascal, and then do the calculations to get this. This is one way. Now, when the section is cracked, now what we are trying to get here is this. Now, the mean strain that I fix, okay, which is your this calculation. So let's say this is your phi effective. This slope and this slope has to be same. So this is your phi effective. So now strain is FSM divided by ES, right? So our in curvature is going to be epsilon SM divided by this distance now, which is d minus x. So epsilon Sm by d minus x is also going to give me phi effective, which is your curvature, effective curvature. And now strain can be converted into stress by stress divided by Young's modulus will give me strain. So I can express in terms of stresses that I'm going to limit in your tension steel. Okay, let's now look at it in depth, how we do this. Okay, now let's look at for uncracked sections. This is what I said. For short term, this stress in the concrete is limited to 1 megapascal. So this is for short term. Now what is short term? Only we are considering the load effects, we are not going to include the creep and shrinkage. So when you do that, code is saying that, British code is saying that you take your stress in the concrete at tension level as 1 megapascal. Okay, so once you fix that, now FSM is going to be modular ratio times FCTS. Now if I fix this as 1 megapascal, what would be this level stress? So what would be this stress? So you can find that this distance is what? Okay, this is at the level of steel. So this distance is basically, what is that? It's going to be d minus x. Okay, so what we are saying is, for small d minus x, it is FCTS. For d minus x, what would be the stress? It is going to slightly become higher than this 1 megapascal. What we are going to take? I have to calculate. This is at the bottom location. This is your FCT. Okay, this is FCTS. Okay, this is your FCTS is equal to 1 megapascal, and this is your FCT. So I have to slightly increase, okay, because it is going to be linear, and I'm looking at this. Okay, so now how do I get this apparent cracking moment with the reduced with the level of 1 megapascal? Then I have to, when FC TS, so basically what is that we have done here is, this conversion is actually equal to FCT. This is what we have done. Okay, so so then it becomes your apparent cracking moment. So stress multiplied by moment of inertia divided by d by 2 will give me m cracking apparent. Now why are we doing this cracked apparent cracking moment? The code is saying that I am assuming cracked uncracked section as only when the stresses are less than this value, which is FCT at the bottom fiber. Okay, because at the level of steel I cannot exceed more than 1 megapascal. So that is what we are limiting. FCT is limited to 1 megapascal, right? Okay, so why is that we are doing that? It is to ensure that when the applied moment is less than but close to the cracking moment, it would be more appropriate to treat the section as a cracked section to estimate deflections. Okay, so what the code is saying, anyway you will have temperature shrinkage issues, and you may also have prior heavier loading. So which, why to take a chance? You take not the cracked moment from your modulus of rupture, you calculate your M cracking apparent, which is a reduced cracking moment capacity, as taking the stress at the tension most fiber as projected stress of from 1 megapascal at the level of steel, that will become slightly higher than 1 at the bottom depending upon your neutral axis depth, that you use it to get your crack moment of inertia. So that is what the code is saying. Now let's say this is what we said for cracked sections to calculate your neutral axis depth. Now for cracked section, okay, now we are looking at this cracked section. For this case, what is it we are saying here is, again concrete stresses are kept as, which is this. So if you look at it, what would be the area of compression force, compression area, half into FC multiplied by, so this is your X, right? And this total stress is going to be half into X into FC, area of this triangle, that I multiplied by B to get your compression force. Now what would be the tension contribution? I am concrete also, I am saying that concrete is also going to contribute in tension, so with the value of your FCT, right? So now what would be the total area? Again, when this is FCT, this area is going to be d minus x, capital D minus x multiplied by FCT. This is your half of d minus x into FCT is your this area, and that when you multiply it by b, this is your concrete contribution. Now what is the steel contribution? Now FSM multiplied by AST, where FSM is the stress in the steel at the location where you have taken that as concrete stresses 1 megapascal. So you can take that. Now again, how do you get your, so if you take your moment about, so tension forces FSM times AST, now you can see that it is going to be D minus X by 3. So this is where your compression force is going to be looking at. So this is your lever arm. So what is this lever arm? Lever arm is going to be D minus X by 3. Okay. Similarly, this is going to be, so where is the compression force is going to be it is going to be b minus x by 3. So that is going to be b into the total force is this. Okay, so that is your moment. So from here, I can calculate. Now we know how to calculate your stress in the concrete at the tension most fiber from the value that I've kept it at the level of steel, which is let's say 1 megapascal, right? So if this basically we are extrapolating it. So this we have seen it, right? Now how do we get this? Let's say this distance is from here to here. It is d, right? From here to here it is small d, right? So and from here to here it is x. Now what is this distance? It is going to be d minus x, which is this, and I want to project it from here to here, which is basically t minus x. So for small d minus x, it is FCTS. For capital D minus x distance, which is higher than the small d minus x, so I can do the similar triangle. I can get for a FCT, right? So once we get these values, once this is kept as 1 megapascal, now using this and this, I can find your neutral axis depth. And once the neutral axis depth is calculated, and I can calculate my FSM as again elastic modulus multiplied by that 1 megapascal that what we have kept. So this also is known to us, right? So then you can calculate the stress. This is your strain. Okay, so how do you get using your strain compatibility? Now FSM by ES is nothing but your epsilon SM, which is your strain, which is this, right? And now what would be the we can calculate now epsilon C. Now how do you get your epsilon C? Epsilon C, you can see if I know epsilon SM, which is at a distance of d minus x. So we can say epsilon Sm is happening at a distance of d minus x. What would be epsilon c? Epsilon c will be divided by x. So from this I can get my epsilon c as epsilon Sm by d minus x multiplied by x. So that is what we have done. Now how to get my stress from strain? So I can get epsilon c strain as stress in the concrete by elastic modulus c. So that is your epsilon c, right? So using this I can get fc as x by d minus x times ec by es multiplied by fs. So then when you simplify that, this is your modular ratio, right? So you can simplify that and find an expression for your x as d by 1 plus fsm by m into fc. All right. So do it in an iterative way, assuming values of xu and making sure that this happens, and then we can. Okay. So let's see what are these parameters. So we have FC as compressive stress in the concrete at extreme compression fiber. FSM is your mean tensile stress in steel, and FC test is the allowable tensile stress in the concrete at the level of tension steel to be taken appropriately. That's what we discussed. It will be taken as 1 megapascal for short-term deflection and zero 0.5 megapascal for long-term deflection. Right? So you're going to take a lesser value of concrete stress, allowable stress. Allowable stress is kept as 0.55 for long-term deflections.